Okay, so let's move on. In the last class, we've started to look at ionic bonding, and we have derived an important equation, which is called the Kapustinski equation. And with the help of the Kapustinski equation, we can calculate lattice energies by pretty simple means. So according to the Kapustinski equation, the lattice energy is just a constant times the number of the ions in formula unit times the charge of these ions over their distance. Okay, so the Kapustinski equation has many applications, and I would like to discuss a few of these applications in the following. So today, now because that doesn't work, I don't know why that is. Wait a moment, I have to fix this. All of a sudden this stops working sometimes, and I have no idea why. Oh yeah, here we go. So first of all, let us look how accurately the Kapustinski equation actually predicts the lattice energies. So lattice energies are not directly measurable, simply because it is difficult to design an experiment in which you basically bring together metal cations in the gas phase and anions in the gas phase to form a solid, and then measure the energy released by this process. However, one can measure the lattice energy indirectly using what is called the Born-Haber cycle, which is an application of Hess law. So let us look at this in more detail. So let us look at an overall reaction, which we react a solid metal with gaseous halogen, for instance chlorine, to form a metal halide, for instance sodium chloride. So that metal halide will be a solid. So this reaction, and this is our overall reaction, will be associated with a standard enthalpy of formation. So now Hess law says that you can actually break up an overall reaction into several steps, and then each reaction enthalpy associated with each step will in the sum give the overall reaction enthalpy. So let us do this. So we can, for instance, take our solid metal and bring that metal into the gas phase. Okay, so this will be associated with a sublimation enthalpy delta H. Okay, so in the next step, we can ionize that neutral metal atom in the gas phase. That will create us a metal plus ion. And again, that process will be associated with reaction enthalpy. In this case, this will be equal to the ionization energy. Okay, so we can also use the look at the halogen, and we can dissociate the halogen-halogen bond to make halogen atoms. Okay, Now, our halogen is already in the gas phase, so we don't have to bring it in the gas phase here, but we need to cleave the halogen-halogen bonds in order to produce neutral atoms. Okay, so this will be associated with a bond dissociation energy. So this bond dissociation energy can be easily measured just as these two here. All right, so in the next step, we can add an electron to that neutral atom in the gas phase to produce a halogenide anion. So this energy will simply be the electron affinity, which is also associated with an enthalpy. Okay? And then we have produced our metal cations in the gas phase and our halogenide anions in the gas phase. And the last step would be to combine these to form a solid salt in the solid state. And the energy associated with that process would be the lattice energy. Okay? So now our lattice energy will be the only unknown in this process here. We know the overall enthalpy. We also know all the other ones except the lattice energy. So the overall enthalpy of the reaction will be, well, the sublimation energy plus the, well, dissociation energy, the ionization energy, the electron affinity, and the lattice energy. Okay. Now we can solve this equation for the lattice energy and then compare that lattice energy with the energy that we can calculate from the Kapustinskii equation. Okay, so now for sodium chloride, you see the results here. So experimentally, you will find that the value is minus 411 kilojoules per mole. The calculated lattice energy will be 381 kilojoules per mole. And you see, while the results are not identical, they're actually fairly similar. All right, so using the Kapustinskii equation, you can calculate lattice energy, and that can be used in order to make predictions whether a particular unknown solid may be stable or not. So for instance, one could hypothesize that a compound of the composition sodium chloride 2 would be stable. Okay, so now the lattice energy could be either calculated by the Kapustinskii equation, or it could also be well, calculated from the Haber-Bourne cycle. So now in this example here, it's actually calculated by the Haber-Bourne cycle. So now what's different to the previous case? Well, for the sodium, not much, there are not a lot of changes. So we still have to bring our sodium into the gas phase. Okay. But instead of removing then only one electron from the neutral sodium atom, we have to remove 2 electrons. So we have to consider not only the first ionization energy, but also the second ionization energy. Okay, for the chlorine, we have to consider now that, well, we need 2 chlorine atoms. So the first step is therefore that we start out from 1 mole chlorine instead of a half mole of chlorine molecules to produce 2 chlorine atoms in the gas phase. Okay, and then 2 of these chlorine atoms need to be, well, transformed into two chloride ions. So therefore, we have to apply 2 times the electron affinity, or the electron affinity for 2 chlorine atoms. All right. So again, the difference between the overall enthalpy information and the lattice energy will be, the difference between the overall energy of formation and the sum of these individual steps will be the lattice energy. Now, in this case, we are talking about a hypothetical compound, all right, NaCl2 that nobody's ever seen. So for that reason, we don't know the overall reaction energy. Okay, so this is an unknown, but now we can actually calculate the lattice energy using the Kapustinskii equation. Okay, and then we again have only one unknown, which is the overall enthalpy of the reaction. Okay, so now again our equation would overall run like this. So the overall enthalpy of reaction would be the enthalpy of sublimation plus the ionization energy, the first ionization energy, and the second ionization energy. Okay, so to that we would have to add the dissociation energy for the chlorine molecule plus the electron affinity of the chlorine atoms. All right, so now the sublimation energy for the sodium is here 109 kilojoules per mole. The first ionization energy is 496 kilojoules per mole. Okay, and to that we have to add now the second ionization energy for the sodium, and you see that this is a very large positive term. Okay, it takes a lot of energy to remove the second electron from a sodium plus. So we have to add to that the dissociation energy for a chlorine molecule, and then we have to add 2 times the electron affinity for the chlorine. Okay, so to that we add now the lattice energy, which we can calculate from the Kapustinskii equation. Okay, and the calculated lattice energy would be minus 2,180 kilojoules per mole. So now we can sum up all these terms to give the enthalpy of formation, which is plus 2,531 kilojoules per mole. And you see that this is a highly positive enthalpy of formation. So that would mean unless our entropic term associated with that reaction would be highly negative, the overall delta G for the reaction will remain positive. And that's exactly the case. So we do not know the exact entropy of the reaction, but qualitatively we can say that when we react solid sodium with chlorine gas to form a solid compound like NaCl2, well, we have less many free molecules and atoms available in the product rather than in the reactants. Okay, so we actually we can qualitatively say that we actually increase the order by bringing these chlorine molecules out of the gas phase and make them part of a highly ordered periodic structure. Okay, so for that reason, we can qualitatively say that, well, because the delta HF is highly positive, and qualitatively spoken, also the entropy should should decrease, our delta G will be negative, and for that reason, our reaction should actually not happen. Okay? So the formation of NaCl2 should be very unfavorable. And that's in accordance with observation. Nobody's ever seen a compound of the composition NaCl2. Okay, so now I would like to point out that in some cases, you will find that the enthalpy of the reactions to form an unknown compound can be negative, but nonetheless, that product can practically not be made. And that is the case when the product is a local thermodynamic minimum and not an absolute thermodynamic minimum, or in other words, it's a metastable compound. So for instance, you could also speculate whether a compound like MgCl would be possible by doing an analysis calculation based on the reaction 2Mg plus Cl2 gives 2MgCl. You would actually find that the enthalpy of the reaction is negative, and that would argue that the thermodynamic driving force for that reaction would be positive, or delta G would be negative. Okay. However, there's another consideration here to make, which is that such a compound can disproportionate into a magnesium and magnesium Cl2, okay, which is also enthalpically favorable. It's associated with a negative enthalpy of reaction, so that basically the overall process, this process plus that process, which gives actually this process, is more favorable than just going from here to this intermediate. Okay? So if you wanted to make MgCl, which could theoretically be possible, then you would probably like to use very mild reaction conditions. Okay? So that any formed MgCl could not further disproportionate into magnesium and magnesium Cl2 over a very low activation barrier. Okay. However, to my best knowledge, the compound MgCl is still not known, so there are no reaction conditions which could actually sufficiently stabilize MgCl that would avoid the subsequent step, the subsequent disproportionation reaction. So a similar example is the reaction cesium plus fluorine. So you could also speculate about a hypothetical cesium difluoride. So now that compound looks unlikely to be stable, but if you do the calculation, you actually would find that due to the high lattice energy, there would be an overall driving force for the reaction. So the reaction enthalpy would be minus 125 kilojoules per mole. Okay? But again, similarly to the above case, this compound would only represent a metastable compound, because there can be a follow-up disproportionation reaction, which is also energetically favorable, into CSF plus a half F2. Okay? So overall, this process here, going from here to here, would be the absolute thermodynamic minimum, and the CSF2 would only be a local thermodynamic minimum. However, that local thermodynamic minimum could be stabilized by performing the reaction under the right conditions. that would basically avoid this subsequent step. That probably also takes somewhat an activation energy can have. All right, so now this is what I wanted to say about ionic bonding. So next, let us go to covalent and metallic bonding. So these two can be described by, in principle, one and the same theory. In particular, a theory which is called the band theory, whereby band theory is a generalization of another theory that you probably already know, which is the molecular orbital theory. So while molecular orbital theory has been made for molecules, the extension of molecular orbital theory to extended solid leads to band theory, and with band theory can then explain covalent and metallic bonding. Okay, so in molecular orbital theory, we can actually only explain covalent bonding because molecules, at least isolated molecules, actually never metallic, but the extension of them, the band theory, can also explain metallic bonding in metals. So let us, in the first part, briefly review the principles of molecular orbital theory, and then extend molecular orbital theory to band theory. All right. So let us first look at the basic assumptions molecular orbital theory makes. It makes actually two basic assumptions. The first one is the Born-Oppenheimer approximation, which simply says that the nuclei rest relative to the motion of the electrons just because they're much more massive than the electrons. Okay, so we consider the nuclei resting relative to electron motion. So the second assumption is that molecular orbitals can be described as a linear combination of atomic orbitals. So a linear combination is a mathematical process. It's actually the vectorial addition, the addition of vectors. Okay, this is what is meant by a linear combination. And the sentence basically says that the addition of atomic orbitals, the vectorial addition of atomic orbitals produces molecular orbitals, and these molecular orbitals can describe the covalent bonding. So mathematically, a linear combination has this form for the example of, well, a molecular orbital formed from two atomic orbitals. That's actually, it's actually not restricted to two. A molecular orbital can also be made of more than two atomic orbitals. When it's made of two, then the resulting wave function that represents the molecular orbital is equal to normalization factor n times the wave function of the atomic orbital A plus the wave function of the atomic orbital B, whereby the wave functions A and B, they have coefficients A and B that designate the relative contributions of the atomic orbitals A and B to the molecular orbital. So the greater these coefficients CA and CB are, the greater the contribution of the respective atomic orbital to the molecular orbital. So this constant here, the normalization factor, ensures that the, well, integral of the square of function, the square of the wave function for the molecular orbital is equal to 1. Only in this case, the probability to find the electron somewhere in the molecular orbital is 1. Okay, so this has to be ensured because the electron practically cannot be found outside of the molecular orbital. At any point in time, it has to be found somewhere inside of the molecular orbital. All right. So a molecular orbital theory, the number of molecular orbitals must always be equal to the number of atomic orbitals. So that means that when we combine two atomic orbitals, we always form two molecular orbitals. One through the vectorial addition of these two wave functions, and one by the subtraction of these two wave functions. This reflects the fact that waves can interfere two ways. They can interfere both constructively and destructively. So the constructive interference refers to the vectorial addition, and the destructive interference refers to the vectorial subtraction of the two atomic orbitals. All right. So now what determines the covalent interaction of atomic orbitals to molecular orbitals? Can we combine any two or more atomic orbitals to form molecular orbitals? And if so, how strong is that covalent interaction that we can expect? And there are actually three criteria that determine that. So the first one is the symmetry criterion. So the symmetry criterion decides whether you can combine atomic orbitals to form molecular orbitals or not. Okay? So symmetry gives you a yes or no answer to that question. And according to the symmetry criterion, a combination of atomic orbitals to molecular orbitals is possible when the anti-bonding and the bond interactions due to the orbital overlap do not exactly cancel out. Okay? Or in other words, the constructive and the destructive interferences due to the orbital overlap, they do not cancel out exactly. Only in this case you can form a molecular orbital from the atomic orbitals. So now, assuming that the symmetry of the two atomic orbitals is right, the overlap criterion and the energy criterion decide how strong that covalent interaction is. Okay, so generally, the stronger the orbital overlap, the stronger the covalent interaction. With regard to the energy criterion, the closer the energy of the atomic orbitals, the stronger the covalent interaction between the atomic orbitals. So now let us look at these criteria in a little bit more detail. And I'm just switching here to the next presentation. So let us look at the energy criterion first. So you see here actually three cases of two atomic orbitals forming molecular orbitals. So in the first case, the energy of the atomic orbitals is exactly equal. In the second case, it's somewhat unequal. In the third case, it's very unequal. So now, let us look at the first case first. In this case, we can form two molecular orbitals from the atomic orbitals. One will be bonding and one will be anti-bonding. And the bonding and the anti-bonding molecular orbital will be about equidistant in energy relative to the two atomic orbitals. Okay, so assuming that we have one electron in each atomic orbital, both of these electrons will go into the bonding molecular orbital, okay, thereby forming a covalent bond. So the bonding molecular orbital has the property that there's an electron density maximum in between the two atoms, okay, while the interbonding orbital has the property that there is a node in between these two atoms. Okay. However, the interbonding orbit is not occupied, therefore the overall situation is bonding. So in the next step, let us make the two energies somewhat unequal. So atom B has now an orbital of lower energy, and atom E has an orbital of somewhat higher energy. So we can still form molecular orbitals, here a bonding one, here an interbonding one. But now you see that the energy distance of the bonding in the interbonding orbital to the orbitals, atomic orbitals of atom A and B are not the same anymore. Okay, so now the energy of the bonding orbital is located more closely it's more similar to the energy of atomic orbital B, and the energy of the interbonding molecular orbital is closer to the energy of the orbital of atom A. So this is now also another consequence, which is that the bonding molecular orbital is located primarily at the atom B, and the interbonding molecular orbital is located primarily at atom A. Okay, so now assume again that we have two electrons overall, one in each atomic orbital. So as we combine the atomic orbitals, these two electrons will go into the bonding molecular orbital. Okay, the interbonding molecular orbital remains empty. So now, because the bonding molecular orbital is localized primarily at B, the electrons will now not be equally shared anymore, okay, or at least not exactly equally shared. So they will be localized primarily at B, okay, even though not exclusively at B. And that means that we do not have an ideal covalent bond anymore, but we have actually a polar covalent bond. Okay, so now let's go to the third case and make the energy difference between the two atomic orbitals very large. So now in this case, we can still form a bonding molecular orbital and an interbonding molecular orbital, but the bonding molecular orbital will be now energetically very close to the atomic orbital of B, and it will be localized almost completely at B. It will actually very closely resemble the atomic orbital of B, but not exactly so. So the interbonding molecular orbital will be in energy very close to the energy of the orbital at A, and will be localized almost exclusively at A. Okay, so now what is the overall bonding situation here? Well, you will have your two electrons almost completely localized at atom B. So effectively, you've actually transferred this electron, which was originally in the atomic orbital of A, to the atom B. So now what you have done is actually a redox process. You have oxidized A and you have reduced B, and you have formed an A plus cation and a B minus anion. And what you have done is actually creating an ionic bond. Okay, so an ionic bond is nothing else but an extreme case of a polar covalent bond. Okay, you can see here again that a completely ionic bond is not possible because the energy difference between the two orbitals, while large in some cases, can never be infinite. So therefore, this electron transfer will actually never be completely complete. There will always be some degree of covalency remaining. Whereas you can actually have a completely covalent bond in which the electrons are completely equally shared. This is the case when the energy of the atomic orbit is really exactly the same. Okay? So now this picture also tells you that bonding electrons are located at the more electronegative atom because the electronegative atoms are the atoms that have orbitals with a lower energy. Of course, you can only combine the same type of orbitals. For instance, a 2s with a 2s or a 2p with 2p. So for instance, a 2s orbital of an oxygen atom would be energetically lower than the 2s orbital of a nitrogen atom. Okay, just because the oxygen atom has a higher electronegativity than the nitrogen atom. Okay, whereas any anti-bonding electrons would be located at the more electropositive atom because the anti-bonding electrons would be in the anti-bonding orbitals, okay, which are localized primarily at the more electropositive atom. All right, then let's go to the next criterion. This is the overlap criterion. So generally, the smaller the distance between the atoms, the larger the orbital overlap, and the larger the covalent interaction. Okay, provided symmetry is right, and we will see exactly what that exactly means in a minute. Okay, so here you have an example of two orbitals that only weakly overlap. Okay, so because of that weak overlap, the covalent interaction is small. What does that mean for the molecular orbital diagram? That means that basically the energy difference between the bonding and the anti-bonding molecular orbital tends to be small. Okay, and the bonding and the anti-bonding molecular orbitals are energetically not very far away from their atomic orbitals. Whereas when the orbital overlap is strong, we get a larger energy difference between the bonding and the anti-bonding molecular orbitals, and the energy difference between the atomic orbitals and the molecular orbitals is also larger. Okay, so then is another important rule. We can say that when we overlap two small orbitals with each other, then that creates good overlap. And when we combine two large orbitals with each other, then that also creates good overlap. If we combine a large with a small orbital, then that creates weak orbital overlap. Okay, so that is understandable when you consider that when you overlap a large atomic orbital with a small one, then only a small fraction of the volume of a large atomic orbital can actually participate. Okay, and for that reason, the interaction of the electrons of the large orbital with the electrons in the small orbital is limited. Okay, so as a consequence, again, in the first two cases, we get a large difference between the bonding and the interbonding molecular orbitals, while in that case, we get a small energy difference between the bonding and the interbonding molecular orbital. All right, then as a third rule, there's a tendency that orbitals that overlap in sigma fashion interact more strongly than orbitals in pi fashion. And that is simply the case because orbitals that interact in sigma fashion, they have orbital overlap on the bond axis, whereas when they overlap in pi fashion, they don't have orbital overlap on the bond axis, but above and below the bond axis. Okay, you can see that here. So here we have a sigma bond, and we have orbital overlap of two s orbitals on that bond axis here. Whereas here we have pi orbital overlap. So in that case, the orbitals overlap above and below the bond axis. So due to the orientation of the p orbitals, that orbital overlap is not as good. Therefore, the split of orbital energies in the latter case here is smaller than the split of the orbital energies in the first case. Okay, so now let's go to the last criterion, which is the most difficult to understand. What is right and wrong symmetry leading to either the possibility of covalent interactions or the opposite, the disallowance of covalent interaction? So let us do this by example. Let's consider the water molecule. In the water molecule, the oxygen atom has, for instance, a 2pz orbital, and the hydrogen atoms, they have the 1s orbitals as valence orbitals as well. Now let's see how they overlap and if actually a covalent interaction is possible between them because of symmetry. Okay? So if it's possible, then the bonding and interbonding interactions would not cancel out, okay? Which is equivalent to the statement of saying the constructive and the destructive interferences do not cancel out. Okay, so now here the algebraic signs of the wave function are indicated by color. So in this case, blue color means a negative algebraic sign, and orange color means a positive algebraic sign. Okay, so now I can see that if we choose our 1s orbitals to have both positive algebraic sign, we can create constructive interference of these two 1s orbitals with that lobe of the 2pz orbital. Okay, there will also be a little bit interaction between the 1s orbital and that blue lobe here, but because the blue lobe is further away than that orange lobe, okay, these interactions will be weaker. Okay, so while there are some destructive interferences also, the constructive interferences are stronger. We can simply see this by geometric inspection. And for that reason, we can say that the interbonding interactions will not cancel out, and therefore this combination of atomic orbitals is correct from the standpoint of symmetry and can lead to the formation of molecular orbitals. Okay, so here we have another example in which we now look at the interaction of the 2py orbital of the oxygen with the 1s orbitals. Okay, so now the py orbital points into the Borg plane. So that orange lobe of the py orbital is, well, in front of the Borg plane, and the blue lobe is behind the Borg plane. Okay, so the two 1s orbitals here are now within the board plane. Okay, so basically half of them is behind the board plane and half of the other hemisphere is in front of the board plane. So now you can see with a little bit effort that each 1s orbital will interfere equally strong with the front lobe, that orange lobe, and the blue lobe, the back lobe. And because the front lobe and the back lobe have opposite algebraic signs, the constructive and the destructive interferences, they cancel out. Okay? So the same is true when you look at the interaction of this 1s orbital with the 2p y orbital. Okay? So there are positive interferences with the front lobe, but there are equally strong negative interferences with the back lobe, and those also cancel out. So overall, constructive and destructive interferences cancel out. And that means that it's not possible to construct molecular orbitals from the combination of a 2py orbital of the oxygen and the two 1s orbitals of the hydrogen. All right, here there's one more example. Finally, we look also at the 2px orbital of the oxygen and its interaction with the 1s orbitals of the hydrogen. So you see, if we choose the algebraic signs of the 1s orbital to be the same, then the bonding and interbonding interactions cancel out. So the constructive interferences between this 1s orbital and this lobe here is equally strong to the destructive interferences between this 1s orbital and that blue lobe here. However, we can choose the algebraic sign of our 1s orbitals to be different, and then in this case, we can still create overall constructive interferences. Okay? Now we have constructive interferences between this orange 1s and that orange blue lobe, and we will have constructive interferences with this blue 1s and that blue lobe here. Okay? Note that this would not be possible. For that case, we could also try to change the algebraic sign of this 1s orbital, for example, but it would not make a difference. Okay? Still, the constructive and the destructive interferences with regards to the interaction of this one orbital with that 2p orbital would cancel out. So regardless how we choose the algebraic signs of our 1s orbitals, the bonding and the interbonding interactions will cancel out. Okay, so now you can see that the inspection of right and wrong symmetries is a little bit laborious for relatively simple molecules. That's still pretty straightforward. But the more complex your molecule becomes, the more difficult it is to make this assessment. Now, for that reason, it is very useful, especially for more complicated molecules, to use group theory and use an approach which is called the symmetry adapted linear combination of atomic orbitals approach, in order to determine whether a set of atomic orbitals is correctly or incorrectly oriented with regard to symmetry. So in the next step, we want to look at this more closely. But I see that our time is already over. So let us stop at this point. And I just stopped the recording.